Hello, everyone. Come on in. Had some more problems with my sound earlier today. Can somebody speak up for me so I'll see if I hear you?
Hello.
All
Good
right.
afternoon.
How you doing?
Good deal. Thank you, everybody. Excellent. And I don't know why I'm showing that instead, but anyways, here we are. Anybody have any questions while we're waiting for others to come in? Remember, you got a test that's out there waiting to be done. Make sure you get that done. I did get yesterday's or Monday's lecture posted, but I don't think I got it. I got it posted yesterday, and I didn't post the notes until this morning, though. That's what I'd forgotten. So you can find those in the Google Docs section now if you need them. Hopefully the video is looking clear enough for you to see it.
Century British coins. They see 16 values, so looks like 16.
Has anyone looked at any of the videos on my YouTube channel that I've made for this course yet? See if they actually look okay.
Yeah,
I mean, some are still a little blurry, but yes.
Okay. I know some of the ones that weren't made for this course were blurry, but I hadn't heard specifically whether the ones for this course turned out blurry. So anyhow, so no one has any questions about the stuff we did last time? We started talking about current, resistance, showed you ways you can calculate resistance. I think the last thing we did was we covered power, where power is equal to I times V. That's the simple answer, but the valuable one is when you remove the V by replacing it with Ohm's law. So if you replace the V with IR, then you get I squared R. That's the one that is important to us to understand why we use AC and why we send such high voltage power lines across country fields. My dog's going crazy. It's okay. Don't worry about it. I'm just saying stuff that don't matter right now anyways. Ain't nobody listening to me, right? All right. So yeah, that's the one. I wanted to explain a little bit about that as we go. So since I don't have any questions, I'm going to go ahead and start in with that, just talking about that power and talking about something that we'll use later, which is a transformer equation. So it turns out that basically magnetic flux happens when you have, well, anytime that you have a magnetic field piercing a point in space, which is all the time. And every time you carry a current on a wire, that wire produces a magnetic field. In fact, if this was, say, the actual wire and the conventional current's going up, if I grab that with my right hand and wrap my fingers around it with my thumb pointing in the direction of the current like this, then when you look at it, my fingers are curling around in the way that the magnetic field goes. So that's actually what the magnetic field does around a wire. If you actually, put little compasses around a wire, you'd see that they say sort of tangent to the edge of the wire. So that happens a lot. Well, that's the reason that you can now take an iPhone, for instance, and lay it on its back on a certain type of charger and it'll charge. It's something called mutual inductance, that basically because you have a coil of wire with current running around it that produces a magnetic field through the middle. That changing magnetic field through the middle produces a magnetic field that penetrates the back of the phone, and it has a coil of wire. That coil of wire makes that magnetic field changing into a current, and then that current is charging up the battery. So you don't even have to plug it in. So that's what these modern inducting chargers are doing. That's what an inductive stove does. If you've seen a stovetop that's inductive, like the weird thing, you can like touch a burner while the water's boiling. You just pull the pot off and then lay your hand right on it. It doesn't burn you. The reason why is because that's an inductive stove. It's using a coil of wire with currents, and they're only going to run in a conductor. So the conductor actually generates quite a bit of current. That current heats up the metal, and that metal getting hot is what boils the water. So let me explain that to you. So we have the problem that P is equal to I squared R. I'm writing this down. You'll see it in a second, but P equals I squared R. That's our big problem. And let me show you why. So I'm going to turn on my document. Well, evidently, I'm just going to turn off the camera altogether. That'll teach you. Okay. All right. And this was really focused a second ago. Now it's not. Okay. So P equals I squared R. So what you have is like a power plant. So this is your power plant. This could be a coal-fired power plant. It could be a oil-fired power plant. Doesn't really matter. It's all just a power plant. And generally, with the exception of maybe geothermal, power plants are essentially places where you boil a liquid to create steam. Steam turns the impellers of a turbine. That turbine then generates electricity by basically having magnets more or less attached to the wings of a propeller. Those wings of those propellers swinging the magnetic field can generate current in loops of wire, and then out comes electricity. Okay. But the big thing is you've got to have some kind of heat source to heat the water to make the turbines turn. And the turbines are more or less our most efficient way of turning mechanical energy into electrical energy. And that's what power plants use. But a certain power plant controls a certain area across the country. So let's say they handle 1 million homes. In general, a home requires 200 amps. So you basically are going to have 200 million amps that need to go out from your power supply. And that's a minimum. I mean, because some businesses take more than 200 amps. Some houses take more than 200 amps. I imagine Nikola Tesla, with all the crap he was doing in his house, had all sorts of amperage going in there. But you're sort of locked at that. Not only that, you're locked at your location. So there's a certain amount of wire that has to come out to this pole, to this pole, to this pole, skip a few, this pole, then to the substation. And the substation is where they break down the voltage again, because what they found out is obviously P equals I squared R is a problem. And if you're going to send 200 million amps across there, that's horrible, right? That's a huge amount of amperage. And this power, what they're saying is whatever current's going through the wire, if you multiply that, if you square that and multiply that times the resistance of the wire, that is how much energy is being wasted per second. Power company doesn't like to waste energy. It likes you to buy all of its energy, right? And it can't, but it can do better. So their plan is, well, I can't control the current because the number of houses times 200 is that. There's no ifs, ands, or buts about it. And I can't control the R either, because the R is basically whatever material I use. Remember, R equals rho L over A. So you can choose on rows, on L's and A's for various parts of your power grid. But at the end of the day, whatever you chose, that's what you got to use. So the total resistance is always going to be unchangeable. So there really isn't anything you can do about that. But what you can do is we can use the fact that Faraday's law allows something really cool to happen. So let's imagine us taking our Pilgrim belt buckle. You guys, of course, probably had a Thanksgiving play that you put on when you were in grade school, and everybody had this big buckle, right? Well, what you're going to do is you're going to take the power inside the power plant before it gets out to here. Take the power, and it's going to wrap around here a bunch of times. Okay. But it doesn't have to be a bunch. It's just normally it is a bunch. So let's say we wrapped it around 10 times. That's great. That's really nice. I'm really happy for you. Okay, we wrapped it around 10 times. Now what I'm going to do is I'm going to take this wire before I send it out. I'm going to connect it to the other side of this belt buckle. And I'm going to do it 100 million times. This is called a step-up transformer. So the voltage that you're sending in some sense is about 115 volts. That's technically what we call the root mean square, the RMS voltage, okay? And in fact, we send it out triphasic, meaning here's one phase, and then that's 90. So at about 60, we start another phase. And then at 60, we start yet another phase. All of those are basically 115 volts. But you can see if you look at the peak of this one, or let's say the peak of this one lining up with the trough of that one, you can get 230 out of it. So that's where the 230 comes from, because you get a net difference of 230 volts from here to here. And that's what will do like your dryer or your stovetop if you have an electric stove. So that's how they get that. But really all they have to send out is 115 volts. But this is called a step up transformer, in that it steps up by 100 million divided by 10. Okay. So when I divide 100 million by 10, that's going to make it 10 million. So instead of 115 volts, it's going to be 115 volts times 10 million. So now out comes 115 times 10,000,000 volts. Now that seems crazy, like, oh crap, now I've got that. And I remember the other equation, in addition to P equals IV, when I replaced I with V over R, I got V squared over R. So you might think, well, this is horrible, but what you got to remember is V is the voltage difference between the power point and the substation / your house. So there's our little house here, right? So that voltage is, again, something that's really related to the current that you run through it. It's not that how high a voltage it is, it's how much the voltage drops. And that voltage drop is going to be a result of the resistance and the current going through it by Ohm's law. V equals IR, right? So by doing this, we've actually increased it to, what is it, 115 times 10 million, whatever that number is ginormous, right? But the cool thing is we're sending out 200 million amps. When you step up use a step up transformer, you step up the voltage by the ratio of the sides, but at the same time you step down the current by the inverse ratio of the current of the two of them. So I divide this by 10 million, 1, 2, 3, 4, 5, 6, that. So now I've only got 20 amps going out. So my power loss went from 10 million, or excuse me, was it 100 million? Yeah, it went from 200 million times the resistance amps squared times, let's say 100 ohms. As we saw, we did 20 or 200 kilometers yesterday, and we got like 6 ohms for copper and got like 10 ohms for aluminum. So it's probably not unreasonable to have on the order of a couple hundred ohms for the resistance. So this is original, and you get 2 million times 100, or excuse me, 200 million. I'm just not used to dealing with big numbers, so I don't want to accidentally say, 20 kabillion, because a kabillion evidently is a real number, but it's actually 20 billion. That's 20 billion watts being lost. Whereas under this new system, we now have a measly current of, I just did that. I did 200 amps. So now I'm going to do 200 amps squared times 100 ohms. And that's going to give me, of course, 20,000. Oh, excuse me. 400, 200 times 200 is not 200. So 200 squared times 100. And that gives me 4 times into the 6 or 4 million. So using just rough numbers, obviously the 1,000 I just pulled out of my ear or whatever, but the main thing is here, by switching from a voltage of say 115 to a voltage of 115 times 10 million, I dropped my current from 200 million to 200 amps. And I went from losing 20 billion watts, that's 20 billion joules every second. Remember, a joule's about as much energy as it takes to lift a red delicious apple off the ground and stick it on a tabletop. So I went from losing 20 billion to only losing 4 million. So that's why the power companies actually use those high tension, remember that's another word for voltage, those high tension lines that are 200,000, 300,000, a million volts up there. And, you know, to service them, for instance, often people are just dropped off with a helicopter directly onto the wire. A friend of mine actually repairs those for a living and makes a really nice living on it. So any questions on that? We haven't studied this transformer equation yet, so that's not part of what you're doing. I just wanted you to know why. And it's a very easy equation, as you can see. You know, it's just, if you go from low turns to high turns, the voltage goes up by the ratio. If you go from high turns to low turns, the voltage goes down by the ratio. All right, no questions on that? Pretty neat though, isn't it? All right, now one of the things you definitely notice is probably the fact that that some wires don't necessarily work. Meaning, if you go and buy, say, a electric edger, which I actually I have an electric edger, which I prefer my gas edger, but it was really nice and a lot less heavy. It's like a, I don't know, it's a cheap tool company anyways. So I had this electric edger, and the deal is you got to plug it up to a light socket, right? So you carry this wire around, which is just really fun, carrying around a skill saw on a long stick that could possibly run over your toe or the wire. But the thing is, when you get that, it'll tell you it's a certain amount of power. And that's all well and good. You don't think much of it, but the reason why they give you that power is because that is extremely important. Okay. And they know you're using AC because about everything uses AC. So here's the problem. Let's say we have let's say we have an edger whose power is 1200 watts. Okay. I'm going to let you stop looking at me for a second. Oh, evidently I'm going to turn the camera off again because that's just what a smart person does. So the edger equals 1200 watts, and you don't think that means much because what would you do with it? It's like not like you know another number or some other equation or something. But what you do know, remember, is that the voltage that we use is about 115. It actually varies quite a bit. That's why people don't nail it down to 120 or 108.5, because as you look at it, if you use the proper voltmeter in your power supply and your electric socket at your house, you find that sometimes it's 118, sometimes it's 114, sometimes it's 220. So that's why we just roughly say that kind of thing. Well, what we do know is P is equal to IV. Because of that, we can calculate the current. And the current, of course, is P over V, which would be 1200 divided by 115 volts. When I do that math, this is actually an example, by the way. So I'm going to do 1200 divided by 115, and I get 10.43 amps. So if you go grab that nice little extension cord that you got from Dollar General that looks like this, literally that's it. It don't even have the third little hole to it. And you can even plug it in from the backside. You get one of those extension cords and you plug that in, you're going to have yourself a nice little fire. Because what's going to happen is that 10.43 amps is way too big for that wire. And in fact, you can look on, usually they print it on some kind of tag or something that comes with an extension cord. Or you actually have to ask the people that are selling it to you, hey, what's the amperage on that? Or you can look it up on the internet and find out what gauge it is. If you know the gauge of the wire, that'll tell you how much amperage it can handle. But 10.43 is a pretty significant amperage. Okay, as I told you, a milliamp, 1/1000th of an amp, can kill you. 10 amps going through something that's rated for maybe 2 amps is going to get it so hot that it's going to melt. And if you happen to be holding the part that melts, then it's going to melt and burn the holy poop out of you. So that's something you need to always do when you're thinking about plugging something in. find out what its power is, whether it's a TV or a refrigerator. You can even just use, most refrigerators have about the same power rating, a little bit different for, really fancy ones, a little bit higher and less high for some of the simple ones with just, barely even an ice maker. So you always check that if you have to use an extension cord, because you want to make sure you have an extension cord that's big enough. The way we don't burn down houses is because we have codes, and codes are one of the great things that government can do. It's one of those things that a government can say, okay, we're going to establish a code, and then that'll keep everybody safe, and because everybody's playing from the same playbook. You don't have Mr. Younger out there just winging it, right? You have every electrician says, okay, well, I know I'm supposed to be able to deliver 35 amps to the kitchen. So, or at least to this particular receptacle in the kitchen. So I know that takes a certain gauge wire. You look it up on the internet or you look it up in the code book, and then everybody wires it that way. A building inspector comes behind you, checks the gauge of the wires that you're using to connect the receptacles to one another, checks the grounds, make sure everything's connected properly, all that good stuff. But that's the way you do it. You can use the P equals IV and just assume the voltage is 115. Notice if the voltage was 120, you would get a lower one. So it's better to use the safe side, the low voltage, when you're trying to estimate the current, just in case it does literally go that low. You will know the maximum type of current to expect. So that's kind of useful. Also, if you have
Well,
go ahead.
I know in some countries they actually require the a fuse in the extension cord.
Yeah.
That way you'll blow that before you actually overload the cord itself. Not exactly sure why in America they don't have that.
That would be smarter for us in America. I don't know why we didn't do that. That is nice, but I guess maybe we don't hear about it too often. Like people usually, I mean, Joe the homeowner doesn't necessarily have a lot of 75 and 150 foot long power cords that he's running, air conditioners through. I guess we don't have that much of a problem with it. I suspect we could, because I'm the kind of guy.
I mean, another thing is, like, companies like certain small cords like that, they'll only make them to like a specific length, which kind of limits you, being able to drag it around outside. They might be like 6 feet or 10 feet or 12 feet, but it's not going to be like 50 feet or anything like that.
Right. Yeah. So that, and that would actually, if you had a longer one, since R equals rho L over A, at least you give a larger resistance and cause a little bit more of the breakdown of the voltage. But yeah, it would be nice to have that kind of thing. But we do have, like I said, other protections. Specifically, they do say not to go over a certain number of amps, but if you don't know how to get your amps from your power, then you're hating it. But also, if you have a generator, like I got a generator for hurricanes and for snowstorms and stuff like that, and it's rated up to 4,500 watts. That's kind of nice, because now I know, hey, my TV runs 120 watts. My refrigerator runs 800 watts. Long as those numbers don't add up to anywhere close to 4,500, then I can run that. And it even has a high amperage output, as well as some small amperage outputs that you can use. So just keep that in mind. That's always helpful. You can also do things like use the power to figure out how much resistance an object has, or something like that. Because now that you got I and you know V, you can now say V equals IR. So according to that, R, the resistor for this 1200 watt device, which could be a heater or an edger or whatever, that R is going to be 115 volts divided by 10.43 amps. And when you do 115 divided by 10.43, you get 11.02 ohms. So you can see this thing that uses 1200 watts really is a low resistance kind of object. In that case, it might be an edger, but I don't remember what my edgers was, but it was, it was something I was able to look up on the web. Let's put it that way. Because you can, put in the model number or something like that. I did find at Tractor Supply a 75 foot cord that was big enough to handle that amperage, but I didn't have a lot of room left over. It was maybe only 10-15% over what it was going to say. So anyways, that's another thing to keep us straight about electricity.
I'll die on you pretty quickly. Careful.
Jacqueline, are you saying something to me, or did you just forget to mute yourself, hon?
Sorry, I thought I was muted.
Oh, no problem. It's okay. I'm sorry about calling you hon. That's just something that happens when you're old and Southern. I shouldn't do that.
Oh, no, you're fine. That's what my grandmother calls me.
Well, thanks. All right. So another thing you might think about is your headlights in your car. For instance, you should know this, but you might not, especially if you drive more motorcycles than you do bikes, than you do cars, because some motorcycles are run on 6-volt batteries. I think the majority of them are 12-volt batteries nowadays, but I'm not positive because I haven't ridden a motorcycle in a while. But cars generally run on 12-volt batteries, and it's a complete DC system. Where the AC stuff comes in is basically when you have an alternator, and the alternator just basically takes the crankshaft or one of the shafts that's spinning, takes a belt off of that and runs it to the alternator. The alternator then spins at that rate and turns little magnets inside of a bunch of coils of wire. Your book has a picture of an alternator, by the way. I think it's not in this chapter though, but anyways, it does that, and that generates electricity to keep the battery charged. Not only that, you don't run it directly off the battery, it's charging the battery and it's running everything in your car. So when your alternator goes bad, you will see your headlights starting to dim and stuff like that, and you might think your battery's dead, but no, it's more likely going to be your alternator that's having the problem. So that's another thing you can do, is you can use that. And by default, whenever you have magnets spinning inside of circuits, you're forcing yourself to generate an AC current and therefore an AC voltage. And this is what they look like. This would be voltage on the vertical axis. This would be time on the horizontal axis. And in America, we use 60 hertz. I think in Great Britain, they use like 45 hertz. That's why you have to get various types of electronic devices to transfer, say your cell phone charger or your hair dryer or any of that kind of stuff you're going to take with you to a trip to Europe. You've got to use a converter to make it safe to use your instrument. So just keep that in mind as well. But that brings us to the issue of AC. So there's AC and there's DC, and then there's AC DC. Bad to the bone. Anyways, actually, I don't even know if that's AC/DC now I think of it, but AC means alternating current. And what we mean by that is it literally alternates back and forth from going left to right to left to left to right to right to left. And the other one's direct current, which is what batteries put out, and the red-black side of the power supply in our lab. Now, oddly, you think everything runs on DC when in fact, on AC, but in fact, most things that you plug in, you'll see almost always have a little heavy box attached to it. Well, guess what? That's us taking the AC power coming out of the wall, and we're turning that into DC voltage to run our cell phone or to run our laptop computer or desktop computer. A lot of the electronics we use are actually running on DC. And to do that, what we do is we allow the two wires to come in. That's how we sort of pictured it with the transformer. Remember, as we imagine two wires coming in, and we send it basically through a diode. So a diode looks like something that allows something to go one way. It looks like you can't go that way, but you can go that way. And that's exactly what a diode does within a certain range. And each diode you buy gives you a certain range and says, as long as you don't exceed this current or this voltage, it'll hold up. So it does that. And if you just did something like that, you would get basically a signal that went from AC. So let's say this is voltage and this is time. The AC would look like this, nice and smooth, about basically the peak current divided by, so this is V peak. If you take the peak current and divide it by the square root of 2, that's the 115 that we use, okay? So that's the root mean square. When you run it through this though, what you've done is you've cut off the negative. So you'll get a series of humps like that. That's a half wave rectifier. There's a way where you can actually connect it to a full wave rectifier by putting another one this way. So when the current is going the opposite way, it actually allows it to come out as well. There's some other parts that have to be done with this, but you can sort of get the idea. Hey, when it's positive, it's going to go through this one, but when it's negative, it can't go through that one because that's like going this way. But this side will be negative, and then that can go through that way. So when you do that, instead, you get like that. Now that's pretty good. You can also, of course, before you do this, you can convert it to a lower voltage. So you could first go through a transformer, and that would shrink it from 115 volts to say 12 volts. Okay. And then you could send it through a full wave rectifier and you'd get that. And what you have is basically this is around 12 volts, which is what your, you know, for instance, your desktop computer might need that. I don't really remember what they run on, to be honest with you. It might be 12 volts, but I'm not sure. But that's not that great because it literally goes to zero, reaches what it needs to, zero, and you get the lights coming on and off, on and off, on and off. So if you now put one thing we call it is you could call it a high pass circuit or a low pass filter or something like that. But really all we're looking for is you put a capacitor to ground there. So there's a ground, there's a capacitor. And what that does is it causes there to be a delay so that voltage can't change that rapidly. So instead of the voltage dropping all the way down to here, it drops, say, to here, and then to here, and then to here. So you get a nice little wobble right around 12 volts. So that's how you make AC current into a direct current. And you'll still see, if you actually look at something that's been converted, you'll see, if you look at it with an oscilloscope or something like that, you'll see that it has a little wiggle in it. And the higher you put that capacitance resistance series here, the less wiggle there'll be, but it's still going to be some wiggle. So that's a little bit about AC, just to let you know, but there's more to it than that. So in reality, what AC does, as I told you, is it basically swings the current back and forth and the voltage back and forth between positive peak to negative peak. And let's say this is the voltage. So if we're calling the RMS 115, you got to remember correctly, that's about 162 volts, 163 volts roughly. Peak. So that would be about peaked out at about 163. This would peak out at about negative 163, somewhere in there. Remember, there is some variation, just like I told you, it's not always 115. It can get to 113 and run up to 220. So if you look over one cycle, though, and that would be for a sine wave, that's just like that, then you could take the integral of the square of the voltage, dt, and divide it by the period like that. And then if you take the square root of that, you would get the V root mean square. And that's where that came from. So your voltage equation might be V is equal to V peak, that's the 163 I was telling you about, times the sine of omega t. And omega, of course, is 2 pi f, which would be 2 pi over the period. And since we're using 60 hertz, you can automatically tell that, well, you could say omega is equal to 2 pi f, and the f is 60 hertz. So that's what the omega would be. It's going to be 2 pi times 60. That's what goes in there. Now you can integrate that squared from 0 to 1 period, and then divide that by 1 over the period. That's taking an average of the square, and then take the square root of that, so you get units back out as voltage, and you get basically the 115. So this is approximately 115 volts. That's where that came from. But as you might imagine, when I say P is equal to IV, that was all derived for basically DC. But it turns out it actually works for AC as well. You can do AC on it. You just have to use what you're supposed to use, which means you can say P is equal to, and this is P average, is equal to IRMS times VRMS. So it looks like the same formula we had before for DC, but we're now adding an RMS to it. You could also say the average power would equal either 1/2 I0, which is what this, that's sort of I peak. I0 squared times R, which you'll recognize I0 over the square root of 2 is the RMS voltage. So you'd say, oh, that's just I RMS squared times R. Similarly, the last one, P could be 1/2 V peak. Your book is calling it V0. So that's why I'm sort of hitching back and forth. All that would be squared over R. But again, that comes from the square root of 2 and the square root of 2. You could absorb that in there. And then you're just going to get V root mean square over R. So all the formulas that we work with in regular DC also work as long as you use the root mean square values. And that's normally what we talk about. If someone says, I remember Mr. Mom or something like that, Michael Keaton saying, he said, yeah, I'm rewiring out. He said, what are you using, 120? He said, oh, 120, 121, whatever it takes. Right? He didn't know anything about wiring anything. He certainly wasn't going to wire it. But whenever people say just a number like that, they're almost always referring to RMS. So the root mean square voltage is, like I said, 115 roughly. That's what we use. So all those formulas are the same if you just use RMS instead of the peak voltage. I think that's about it regarding whether or regarding AC power. One thing I wanted to do is talk to you about how wires or how houses are wired specifically with electrical sockets and things like that. If you actually take and look at electrical socket, it actually has a lot of cool stuff on it. So I don't have one in here in my room right now. I wish I did. That should be something I add to my collection of crap. But anyways, if you look at a receptacle, it looks like this, and it'll have a short side, and it'll have a long side. And to me, it looks like a drunk, angry person. What are you doing? Yeah, right. They don't have some little white plastic sometimes. Sometimes it's just black in there. But then you get exactly the same thing on the one below that. And again, it would be a short, a long, and then this guy down here. And I can't remember because I don't do this that often, but I do know how. And I just remind myself, I can't remember which one has the gold screws, if it's the short one or the long one. But one of them is supposed to be the hot wire. The other one's supposed to be the neutral, which is really what the current's supposed to return on. So I'm thinking this is the hot. And if that's the case, I think that's the one with the brass screw. But I'm going to put a question mark over it just to remind you that, hey, Mr. Younger does not do this for a living. So there's a high probability that I got this scrap reversed. And then you got a silver screw over here. And it's not silver, the metal, it's like zinc. It's just a piece of crap, right? And there's another one over here. And in fact, if you look at it, it'll have like this little thing will come down here and it'll go out here. And then it has these little brackets like this. And it's got a little thing you can put a screw in. And it's got a little doohickey like this. Well, that thing can actually allow you to strip your wire. So those little parts right there are something useful. It's not very good of a stripper, but it can allow you to strip your wire. If you turn around the back of this thing will have, for instance, a little gauge right here that tells you how long you should strip it. And in fact, it's also got like a hole in there. So once you strip it, you can just jab it in there, and that does the same thing as connect it to a screw. So there's a lot of different things you can do with this, but it's super, super convenient. Once you open up the actual receptacle and look at it inside, it's such a perfect place that put these screws, because when you go to grab it, your hands are just the right spot. If you grab it there, it is going to light your world up. Okay. So be careful of that. Once you take that plate off of the receptacle, these two things are very hot and they're very different, right? One of them's the hot side, one of them's the neutral side, and then there's actually another one that connects, by the way. I think that connects up here, if I remember correctly, and that's a green screw. That's the ground. So they have a neutral, which is usually white. They have a black, a hot, which is normally black. and then they have a ground wire that can be green or bare or various other things. Okay, now the ground wire runs to this and this, and in fact all the ground wires run to a common rail in the back of the circuit panel that then runs to a really big wire that goes out. So here's this, it goes out, and there's a, I think it's either 6 or 8 feet long, meaning I can't remember which one it is, but it's a basically a copper clad. It's covered in copper. It's probably zinc in the middle. And you take that thing and you stick it in the ground and you literally drive it down till it's flat. And then you take the wire and you connect it to a clamp that clamps it onto that. And that's supposed to be where all the electricity goes when you do something stupid, right? Like if you accidentally drop a heater or a hair dryer in the tub, it's going to kill you. It's a high probability that it can kill you. But luckily, bathrooms, receptacles in bathrooms tend to be what we call a GFCI outlet. That means ground fault circuit interrupt. And whenever it notices a huge surge of current going through, it automatically has a magnet set up in it that is being driven by that huge current. That huge current will make that magnet become really strong, and that magnet becoming really strong will cause something to flip, to disconnect it, and it's going to take the return current wire and the ground wire and connect them both, or excuse me, and the black wire, and connect them both to the ground wire, and it sends it all straight to the ground and keeps from electrocuting you if it works like it's supposed to, which it's supposed to, right? And if you're in an old house, they don't have GFCIs, and they don't have to put them in until they have to do amount of work that's comparable to the value of the home. It would be good if you're renting a place to put them in yourself, if you can. But like I said, it's a really good thing to have, is these GFCIs, and that's what they do to save you from, you know, dying. We also have older houses will have fuses, and what that means is there's a copper ending for a wire that runs to a power supply, or runs to a power supply, say the telephone pole, and there's a copper ending that runs to all the receptacles in your house, or all the receptacles on that leg. And then you take and you put a fuse in there, which is basically just a little ribbon of metal. And that ribbon of metal has a certain thickness and a certain width. And the people that make the fuse have discovered that if that current exceeds, say, 15 amps, then that metal ribbon will melt in two, and that stops the circuit. That stops, it opens the circuit and causes the current to stop flowing. So it's not a good idea to replace this with a screwdriver shaft. Okay. People do that. Do not do that. It's not good to put pennies in there, any of that kind of stuff. All these things are meant to protect you. The other way is they use circuit breakers, and that's sort of like the device I was just telling you about. We can make an electromagnet if we take the wire that comes from it and wrap it around it a bunch of times, and then connect it to this. And then let's say this thing is touching this metal part right here. So all the current's supposed to go around this magnet, along this metal bar, through that little metal plug, and then touch this, and then go out to the house. However, if this current surges a lot, that's going to make this magnet really strong, and it's going to bend this flap. So this flap goes over like that, and it disconnects the circuit. Does that make sense? So that's how those things work. And I think that's very helpful for you to know, just to know why they do it the way they do. In fact, I once made my own little setup. I took a wall receptacle, you know, short and a long, and I did the equivalent of this. Now, do not do this at home, but I did the equivalent of this. I stuck one wire in there, and then I took a little piece of PVC and put it around a steel rod, like a horseshoe stake, basically. Okay, so this is a steel rod. So that I'm making an electromagnet once I wrap the coils around it. And then I put a little Teflon cylinder around it like this, so it made it like a spool. And I put another Teflon spool around this end, so I had nice, neat ends. And then I wrapped it around this. about 1,200 times. I did it with a lathe. Okay. And then I took the other end of the wire, and normally you just stick it right in the receptacle and it works, but I really wanted to not come on all the time. So I used a Morse code device. So I connected this to a piece of metal. It had a piece of metal like this with a little knob on top of it. And then it had another piece of metal like that. And I completed the circuit just by pushing down on it. So it's like a little Morse code. So, and then I ran this piece of wire into that hole. Actually, I put a variac on it so I could boost it by about 120% because I didn't want to do no wussy kind of thing here. So when I did that, then you can take a cylindrical disc made out of aluminum on it. And I would take that aluminum disc and dip it in liquid nitrogen so that its resistance would become really, 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 really low. What happens when I connect this circuit, current runs through here that's AC, and the instant the AC is going around this way, it's inducing a current going around the opposite way in this, and they repel each other. And then it switches to going around this way, and then this one switches and goes around this way, and again repels this. And by doing so, I was able to shoot this thing up about 65 feet. That's basically an electric rail gun, if you will. Okay. The problem is, well, there's a lot of problems actually. There was an evacuation that day. We'll just say there was an evacuation of the physics and biology department that day, because it turns out that there's ratings on switches for Morse code. And when I actually closed this, it welded shut because it was so hot that the metal melted and froze it shut, and I couldn't get it apart. And then that much current going through there actually melted the PVC, which, you know, happens to be carcinogen. That made a really bad smoke that was carcinogenic and filled up 2 floors of the physics department, and then started to waft over to the biology department. And that was all me. So it turns out switches are rated too, so you should look for those, right? You can't just use a light switch when you build something like this to connect it. In fact, I found I figured out how many amps I was running, and then I found a switch that greatly exceeded the amperage that I was using, and I made this thing again. This is called Elihu Thompson. Elihu Thompson's jumping ring. He's an interesting character by himself. He was an engineer and a physicist during the time when we discovered radon and curium and all that stuff. And he was convinced, like most of the scientists were, that there was no harm from radiation. So he decided to, use the scientific method to prove to everyone that in fact radiation is not harmful. X-rays are not harmful. So he took an X-ray tube and he laid it on his finger for like a whole minute every day. And he wrote down in his logbook, today's day 7, still no effects as suspected. X-ray is, not a bad thing. It's not going to cause any harm or anything like that. By day, I think it was like day 62 or something. He says, my finger is a festering boil of pus and smells like death. I have stopped the experiment. Evidently, the X-rays are dangerous. And then like 3 years later, his finger is only now back to a normal state. So Elihu Thompson's a pretty neat character, and at least he's
Professor.
What's that?
Professor, going back to your coil gun you made,
right?
You might be interested to check out. There's this company called Arc Flash that
ART or ARC?
ARC.
Okay, Arc Flash. I think I know them.
They have
Tesla coils.
They have a commercially available Gauss gun.
Oh, cool.
That actually functions. It's a little over $3,000, and its velocity is like 300 feet a second. It's not quite like the type of firearms and everything, but it is commercially available and you can buy it. And it's kind of an illegal gray area at the moment.
Yeah, like 3D printed guns and stuff.
Yeah, the size projectile too. I mean, you can vary like the sizes of them and everything, and get different performance out of it. Cool. But yeah, it's commercially available and you can purchase it.
Cool. I didn't know they did that. Yeah. I'm pretty sure that's the company I saw that makes commercial Tesla coils as well. I remember it having a weird name, like I thought it was Art, so I'm wondering if it might be the same company. But yeah, I'll definitely.
Yeah, it might be. I don't know. I've seen a few reviews on YouTube on it, and I checked the company out, and I was like, well, damn, that's right. They are selling this. That's so
Exactly.
weird.
That's crazy.
Kind of clunky, but you know, it's a fully functional Gauss gun. Kind of
Yeah,
interesting.
that's pretty cool. If you do try to make something like this, you want to use a not too big of a gauge of wire, because that's going to allow a lot of current in there to get hot. But you also want to use a housing, a coil with a wire with actual housing around it, as opposed to just a laminate cover. You also want to only have it on for a split second, on the order of 1/10 of a second, or maybe up to a 1/2 a second, because it gets really hot really quickly. You're drawing so much current. I actually blew out my circuits of my house several times, or flipped my circuit breaker several times playing with it. So it's not the safest thing to play with, but it is interesting to do. Any questions on that cool introduction to AC and all the dangerous stuff you can do with electricity? So now you know a little bit about how we wire our homes. Oh, I didn't get to the part that I was meaning to, because I got on all those cool side stories that I thought would be interesting too. But now, how do we line up these receptacles, and then how can we tell if we're doing something stupid or not? Well, that all depends on understanding that light receptacle, or that receptacle I just drew for you. So imagine this is the receptacle again, and the way you actually wire it is, this is the wire. You'll take the black, and it's going to go to one screw. Again, I think it's the gold screw that it goes to. Again, I'm not remembering exactly. That's something you should check out before you just blindly trust me, because again, I don't do this for a living. And the last time I wired something was well over a year ago, and I just check it on one of my little engineering electronics books. So maybe this is the black wire right here. That's attached to that. And you might have wondered, why do we have two screws over here? You know, why do we have the setup there and then a setup here? And then here's the ground right here. So we take the bare wire and connect that to it. So that's the ground. Okay, and the white wire we attach to that. This is actually a really convenient setup, because now you can take and connect the white wire from it to another screw on this side of another receptacle. And we can take the black wire from, connect it to this. I just literally just bought this pen. It should be brand new, and it's acting like it's running out already. So this is the black wire coming around here to this screw. And of course, the ground wire would also come around and connect from here to here as well. So you still have the ground, but the main thing is, what you see is whichever side's the high side, that's connected directly to the high side of this one. That's connected directly to the high side of the next one, so on and so forth. That's the beauty of it. So now you can see that if your power source, and this is the way we draw an AC. Oh, I'm actually drawing this without you looking at the diagram. Stupid me. Okay. So what I was drawing was, this is supposed to be the receptacle. Like that. And I'm assuming again that the black goes to the side. I'm reminding you that I don't remember for sure about that, but we do the same thing again over here. We have another white wire coming from this one, another black wire coming from this one. And we can line all those up. All of our light receptacles are all rigged that way. And by having consistently the black side to the right side, what you're getting is, here's a power supply. You sort of treat this as the black side. It comes up and it runs to a resistor. And then the black wire goes to the next resistor, which again is another light socket, and another light socket like this. And then the white wires all go here, 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 like that. So what you're seeing is that, in fact, light receptacles are connected in parallel. So they're all connected in parallel. And that's good, because if they were in series and one would burn out, then all of them would burn out like old Christmas tree lights. Okay. That also means that everything has the same voltage. Everything's at that 115, 120 volts. So you might say, well, why does my circuit breaker break? Well, let's imagine this scenario. Let's say I've got several things plugged in to a single receptacle. Let's say I have a light bulb, and that's 100 watts. Of course, that's also 115 volts. Let's say we have air conditioning, an AC unit. That's going to be like 2,000 watts. Again, 115 volts. If you plugged a window AC unit in, you're going to be using 2,000 watts of electricity. You also might have a radio plugged in, and that would be about 300 watts, say. I'm old, so we listen to rather quiet stuff. And then my wife decides that she's going to blow dry her hair. And hair dryers are a heater plus a fan. So that tends to take up quite a bit of wattage. That's 1,200 watts. Okay. Again, 115 volts. So if you actually connect a wire or your receptacles with a specific type of wire, it has a specific rating on how much current it can draw. And a typical current, for instance, might be 15 amps or a 35 amps or something like that. So let's say this is a 30 amp service. In other words, we used a wire that's capable of holding 30 amps to connect all the receptacles that these things are plugged into. So what we have now is we have 4 items that are in parallel with 115 volts. Like so. And what we got to figure out is what the current. Well, the current, since P equals IV, we know that I is equal to P over V. So that's going to be 100 over 115. In this case, it's going to be like 0.97 or something like that. No, 0.869. So 0.870, 0.870 amps is that one. That's for the light bulb. The current for the AC unit is in fact 2,000 divided by 115. Well, 2,000 divided by 115. That gives me 17.39 amps. The amps for the radio, I realize now I'm writing too low. The amps for the radio is about 300 divided by 115. That gives me 2.61. And then the wife plugs in the hair dryer, and that gives me 1,200 divided by 115, which is the same thing we got for the edger earlier. 10.43, I suspect. And yes, that's 10.43. So what you did was basically you put 4 things in parallel, and each of these sort of act like a resistor. What happens to the net resistance? Like if I made an equivalent right here, does anybody have an idea what would happen to what would be the equivalent resistance of this? Is it bigger than each of them? Is it bigger than the sum of them? Is it equal to the sum of them? Anybody know?
The equivalent resistance would equal the summation of the other. Wait, no. There's it's the same as it's the same as the series capacitors equation.
Exactly, except they're reversed because the capacitor has the ones in series. Their reciprocal add to give the reciprocal, but the parallel ones just add. These in parallel add as the reciprocal. So in fact, the net resistance will be smaller than the resistance of either one of any one of them. And that small resistance means a big current's going to come in here. And you can see that right now because look at the current. The current's about what, 10, 12, 29, 29.8, 29, 30.2, 30.8, 31.2. So this is already I total is greater than 30 31.2 amps. Actually 31.4 amps. That's just me adding off the top of my head. So I can already tell the circuit's going to blow. And that's how circuits generally blow. You could look at it by first calculating using the power and the I squared R or the V squared R. That could calculate the individual resistances. And then you can put all these resistances in parallel. And it turns out that 1 over the equivalent resistance in parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. And what you'd see is the net resistance is really, really small. If you say V equals IR for that, then you're going to get that the I is the V divided by a very small resistance. So you'll get a large current. And that large current is what we just saw is exceeding 30 amps. So that's how you end up either burning up a fuse or flipping a circuit breaker, or if you were wise enough to have stuck a screwdriver in place of your fuse, that's how you burnt down your house. So don't do that. That would be really bad. Any questions on that? So I think I've covered just about everything now. We'll do more with AC a little later once we learn more about other AC devices like an inductor, and we already learned about a capacitor. But what I want to do now is spend this last few minutes to give you a microscopic description of current. So what we know, for instance, current is delta Q over delta T. At least that's our average current. Right. And we need that, right? So if you take a chunk of wire like this, and you imagine it has an area given by, say, A, and a length by, say, L, like that, okay? What we need to know is basically the number of charges you have free to move in there. So I need to find how many charges will be moving by. So I'll start to look at delta Q, and delta Q should be the number of charges times the charge per particle. So the particles are actually going to be electrons. So we have to find the number of electrons times the charge per particle, which is the charge of an electron. Well, you might think that if you took the volume of the actual container, in other words, of this complete wire, and use that density of the number of particles per volume, then you could say, wait a second, I'm going to say this metal right here has N, which equals the total number of particles in a volume V. So that's sort of a density, if you will. So I can say this delta Q is going to be little n, as I defined right there, times big V. And then I've got to multiply that by the negative E, which is the charge of the electron. Okay. So I've got to figure out what that N is, and we can actually do that. But what we can also do is we can figure out that the volume of this is really the length times the area. So I can say the N, the number per unit volume of charge carriers. Now that's going to be basically most atoms of a conductor tend to have one free electron per atom. So you're really just calculating the atom of the number of atoms per unit volume, which I think you can figure out a little bit how to do. But some of them have 2 or some fraction of 2 on average carriers per atom. So with this case, what I'm going to say is, let's imagine, in fact, that the particle is going bang, 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 all these different ways, bouncing off of all these atoms. The net effect is that it has some kind of drift velocity, V sub D. Okay. So the volume can be written as A times V sub D which is a vector quantity and can be treated as a vector quantity. And then that V sub D times the time that you're actually observing it. So I'll call that delta T. So now I can say that I, at least the average current, is delta Q over delta T, which gives me N, oops, I left off my negative E, which gives me N, the number per unit volume, times E, times the area, times the drift velocity. Now there happens to be something called the current density, which is a vector quantity. So if you were carrying, say, 20 amps, you would take 20 amps and divide it by this area A right here, and that would give you the current density. So I could say that the current density J is actually equal to I over A, in which case I'd get negative N times E times the drift velocity. And the fact that it's negative just tells us, hey, conventional current is the direction that positive charges go. So it's got to be the negative of this, because this is the direction that electrons go. And we just find that. So that's an actual microscopic description of the current density in terms of parameters that in principle we can calculate. So we can use this now to calculate for a given current, a given type of wire, what this drift velocity is. And if you've ever watched the movie Arthur, you know that one of his apartments that he was looking into renting, because Arthur was super, super rich, and then he wanted to marry a commoner, and he lost all his inheritance because he married a commoner, and basically had to live on whatever means he could get. And he was looking at apartments, and he had found that this one apartment for rent had IOL, and they didn't know what it was. And he got there, and the old codger told him, it's instant on lighting. Like, as soon as you turn on the switch, the lights come on. So that might make you think that like the speed of light is how fast the particles go, but it turns out it's not really that fast at all. So let's imagine a copper wire. So here's another example. A copper wire. And let's say it's going to carry 10 amps. And its diameter is 0.500 inches. Okay. What I want to know is, assuming the wire is at about 20.0 degrees Celsius, what is the drift velocity? Okay. So what I know is that I is equal to 5.0, or excuse me, 10.00. I was mixing it up with my diameter. Is 10.0 amps. I know that my area is pi r squared, which would be, notice notice r would actually be 0.250 inches, and then 1 inch is equal to 2.54 centimeters. So 2.54 times 0.25 gives me 0.635 centimeters, which I actually have to convert to meters anyways. So I'm going to say this is pi times 0.00635 centimeters squared. So I'm going to square that times 3.14159. That gives me an area equal to 1.267. Oh, no, it doesn't. I'll list some zeros in that. That's 0.635. Sorry about that. That's 0.635 centimeters. So 0.00635 squared times 3.14159 gives me 0.00127 square meters. It's supposed to be 126 times 10 to the negative 6. So 10 to the negative 6 would be 1, 2, 3, 4, 5. Oh yeah, I did another 0 in there. Okay, so that's the area. Now we got to figure out all the other stuff. Well, the J, which we now know, is going to be 10.0 amps divided by 0.0001267 square meters. That gives me 78.94 times 10 to the third, and that's amps per square meter. Now that is big, but remember, we're not talking about a square meter of wire here. We're talking about 0.0001267 square meters. So that's a very small area. Now, how do we figure out the number density? Well, the number density N is really the total number of atoms, if you will. If we assume one carrier per atom, 1 E minus per atom. If we assume that, then it's just Avogadro's number divided by the volume for a mole of the substance. So a mole of the substance, of course, is a certain mass. So we can take, in some sense, and calculate the number of them for a single mole, which is Avogadro's number. And we could say that's in Avogadro. But density, this is the mass density now. Mass density is equal to mass per unit volume. And that's 8,960 kilograms per cubic meter is the density of copper, right? So I can say that V is actually equal to M over rho. Well, the mass of a mole is in fact the molecular mass, or in this case, the atomic mass. And for copper, the atomic mass is 63.546 grams. So we'll say this is the M copper divided by the density of copper. So ultimately we get Avogadro's number times the density of copper divided by the molecular mass, or the atomic mass of copper, which I said was 65.436 grams. So this is 6.022 times 10 to the 23rd per mole. Say E minuses per mole. This is 60. Let me double check that. I was looking outside of my eye anyways. Copper 63.546. That's going to be 0.063546 kilograms per mole. Because remember, that's actually grams per mole is what the periodic table gives us. And then times the density, which is 8,960 kilograms per cubic meter. So that should give it to us. That will actually give us number of electrons per cubic meter. When I do all this math, I get 6.022 e to the 23rd times 8,960, and then divided by 0.06356. And that in fact gives me 84.91 times 10 to the 27th E minuses. Sorry about that. E minuses per cubic meter. Okay. So now I know J, we just derived this, J is equal to, at least in magnitude, NEVD. So that tells us the drift velocity. And basically the fact that I use this particular value of the density of copper and this particular value of the, well, not that one, but just that one, means that the copper was assumed to be roughly 20 degrees Celsius. So the drift velocity should be equal to the J divided by N times E. So the J we already found was 78.94 times 10 to the third amps per square meter. The N we found was 84.9 times 10 to the 27th. And that was E minuses per cubic meter. And then the charge was 1.602 times 10 to the negative 19th coulombs per E minus. So you see the E minuses cancel out. The meters squared cubed in here comes to the top and divided by meter squared. So that just leaves a meter there. And then we have an amp, which is a coulomb second. That coulomb's a coulomb per second. That coulomb is going to cancel out with this and leave a second in the bottom. So all the units work out wonderfully. And we get the drift velocity is, so I'm going to take 78.9 divided by parenthesis. So I took that number over there. Now I'm going to take this number and I'll multiply it by 1.602 e to the negative 19. And I get 5.803 times 10 to the negative 6 meters per second. This would actually turn out to be, if I converted it to say, let's say, okay, is that 5.803? Yeah, I did get that. So that's 0. Well, actually, let's convert this to kilometers per hour. That might be interesting. No, I'll do it to millimeters. So I'm going to convert it to millimeters. So basically, I'm going to take 10 to the negative 3. That's going to make it a millimeter. So I'll say 0.005. That'd be 1, 2, 3. So that's millimeters per second. Not very fast at all. And in fact, if you had thermo already, you'd know that V root mean square speed of this is supposed to be 3 kT over m, where m is the mass of the electron. That turns out to be roughly, well, we can write it in here, 3 times 1.3807 times 10 to the negative 23rd joules per Kelvin times 298 or 293 Kelvin. You had chemistry, you might have also seen this before, and 9.109 times 10 to the negative 31st kilograms. That's the mass of the electron. When you do all that math, that turns out to be about 1.2 times 10 to the 5th meters per second. So the velocity of the drift particles going by due to the current is really, really, really small compared to the average, velocity they have just because they're moving in random motion due to temperature. So that's pretty remarkable. I don't think I made any mistakes. It looks about the right size. I use, most of the time I get on the order of 1/10 of a millimeter per second. This time I got 10 to the, I got 0.005 millimeters, but that might be a result of me using a really big amperage and a really small wire this time. Normally the wire would actually make that a little bigger, but anyways. So yeah, I guess that might have been the part of it, because I made the wire so small, not many part charges can flow through there per unit time. But I think that's a pretty good end to chapter 25. We did skip, and we are skipping the last two sections, section 25.9 on superconductivity and 25.10 on electrical conduction in the nervous system. If you're thinking about medicine, I would definitely recommend you reading those that last section. If you're thinking about engineering materials or material science, condensed matter physics, anything like that, then you might want to go ahead and read over that superconductivity thing. But other than that, you guys are free to go. Don't forget to do your tests. You have the test coming due. There's a lot of videos on my YouTube channel, and I've not noticed a huge amount of traffic on it, so y'all might want to look some more examples up. But everybody's free to go. Stick around if you have any questions. I'll be here until the last person leaves.
Professor,
Yes.
my internet was blotchy on Monday. I missed the part where you're talking about test 2. There's 2 dates on it. Is it the 14th or the 10th?
It's the 14th. I moved it back, I think,
Okay.
because there were some problems. Let me double check that while you're here, just to make sure I'm not telling you something wrong. I'm going to look in quizzes, see what I've got it set to. Be there in a second. Hold on. I remember moving it back, so I'm pretty sure it's the later date, but I just want to make sure I don't tell you wrong. So this, you've already done test 1, right?
Yeah.
Okay. Yeah, this seems to be due February 14th at 12:01 a.m. Notice that's 12:01 a.m. So really you have to do that on the 13th.
Okay. Because at the top it said the 14th, and then big red letters that had the 10th on it.
Yeah, that was where, yeah, that's where I originally said it, but it's notice it's 12:01 a.m. That was me trying to get it consistent with the syllabus, because I said the morning of the day that actually appears on the syllabus. So the only way I could make that reasonable is to do like 12:01. I don't want it to be like 8 a.m. or something like that, because then a student might, miss a class just to finish the test. So I just barely pushed it past midnight, so it would be technically on the same day as class, but you always assume it's going to be one day before, which is February 13th in this case.
Nope, that sounds perfect. And then there was no practice test listed.
Oh, well, let me check that too then. That's supposed to be there. Good thing I gave you till then to do it. I thought I had 1, 2, and 3 all the way up. Let me check that right quick.
At least for me, I didn't see it. I sent you an email on Monday about it.
Okay, let me see. Oh, yep, it's not been selected at all. It was on there, but it's not what we call published. Let me make sure everything's working on it. So I'm going to edit it. It's up there now. That should be plenty of practice, since you have, the 14th. Today's only the 9th. You've got plenty of deadline.
Yeah,
on.
no, I kind of set like one day aside. I do like a bunch of them, take notes on it to study, kind of make a little study guide out of it.
Gotcha. Yeah, so I've now got it set to February 13th at 11:59 p.m. That way it'll remind you, hey, I need to do my test by then.
No, I appreciate it.
Thanks for catching that for me. I appreciate it. Feel free. I told my students I actually put my cell phone number on there for you guys in case you actually email me like that. You don't hear back from me within one school day. I totally want you to text me at that point, so that way I can, get the message. I'm not ignoring anybody's emails on purpose. It's just me missing them.
I get it. No problem. You're busy.
Well, thank you. Have a good day.
You too.
Anybody else? Darren? It looks like it. I guess Darren's.
Yeah, I'm good. I was just trying to make sure everything was set for the next one.
Okay. Thank you,
Thank
Darren.
you. Have a good night.
You too. Bye-bye.